It is my great honor to be able to introduce Dr. Steve Boggs of the University of Connecticut. Steve Boggs is going to be our lecturer in this plenary session this morning. And the reason he is the plenary session speaker is because he is the 2010 award winner, Dakin Award winner. Okay, now for those of you who might not know, the Dakin Award is named after Dr. Tom Dakin, who was one of the pioneers in this field. And the award itself is, in fact, the highest award that the IEEE Dielectrics and Electrical Insulation Society can bestow. It recognizes the outstanding technical achievement of an individual in our field. The actual award will be presented tomorrow night at the awards dinner and by Dr. Julia Kokichi, who is currently the DEIS president. And I think she will at that time give a little bit more introduction to Steve, a little bit more formal. Okay? For now, what I'd like to point out is that Steve got into this electrical insulation field about 1975. He joined the research division of Ontario Hydro back at that date. He was a young physicist at that time. I know he doesn't quite look too young now, okay? But he seems to be aging better than I am. Anyway, you know, this dielectric aging thing going on. Anyway, I also, it turned out, joined the same group at Ontario Hydro Research at that time. And in fact, over the next 15 years or so, Steve and I worked on many projects together in the electrical insulation field. And in fact, we shared our offices for about 10 years, which is why I have rather advanced signs of aging right now. I'm sorry, Steve, I didn't mean to say that. That was in the first draft. Okay? Okay, so Steve brought a lot to this field. Of course, he had his tremendous fundamental understanding of physics. That was his training through school. He had a lot of experimentalist skills. He started off as an experimentalist. He was a workaholic. Okay? You still get emails at bizarre times of the night and day from him. Okay? The guy just works incessantly. And most importantly, he had a tremendous amount of curiosity and, as many of us know, tremendously innovative. Okay? He's been active in many areas or aspects of electrical insulation, including partial discharge, the physics of breakdown, high electric field theory. And of course, this has been applied to many types of insulating materials, including cables, capacitors, gas-insulated switchgear. After being in industrial research for about 20 years, Steve joined the University of Connecticut, first at the Electrical Insulation Research Center, which he now leads. This allowed him, being in the university setting, allowed him to expand his fields of interest and, in fact, migrate to do more theoretical work and computational work, which has been his main contributions for the last few years. Of course, he also then had a lot of interaction with students, and I know there are many students, some of them who are here and former students of his, who are still very active or very active in the electrical insulation business. So he's mentored a lot of people through the system. Okay, what I'd like to kind of conclude is by saying I'm actually glad that Steve is here, okay, and he's alive and kicking, because I'm going to tell you a little bit of a story. It actually doesn't reflect very well on me. But you know, a long time ago, it turns out that we didn't really follow safety rules too well. Okay? And all of the young people here ignore what I'm saying. Okay? You really have to follow the safety rules. But there was a tendency for us to go in and go within the high voltage enclosures where there'd be high voltage and we'd be doing experiments and stuff. And Steve and I were in an electromagnetically shielded room one time, this was many years ago. Actually, for me, doing actually real work for a change. And what happened is that Steve wanted to look a little bit more closely at an object that we were aging, a test object. And of course, I guess we were working around 60 or 70 kV. And he asked me, Greg, could you turn off the voltage? Well, I was kind of brain dead stupid, and I forgot. Okay? I know, all he did, simple question, please turn off the voltage, and all I had to do was turn the variac. I forgot. It was an accident. It really wasn't intentional, okay? So what happened then is Steve, with his outstanding knowledge of electrostatic theory, as he got closer to this energized object, happened to notice that the hairs on his arm started to rise, okay? But you need a lot of theory to know that one, that means there's high voltage still present, okay? And he backed away, and he very calmly asked me, Greg, did you turn off the voltage? And I hadn't. Of course, I did turn it off at that particular point. Anyway, Steve is still here. He wouldn't be giving this lecture today if he hadn't been able to detect that there was a high voltage there. And I'm really sorry I did that to you, okay? That's why one of the reasons I lost my hair. Okay, anyway, I would like to welcome Steve up here to give the lecture today. I think he is one of the most innovative people we have in our business, and certainly one of the most productive. And Steve, please come up and give your paper toward a fundamental understanding of conduction in electrical insulation, and I hope I understand it.
Thank you, Greg. Actually, I remember that instant better than you do. I was in the high voltage cage because we were using an image intensifier, and I needed to be close enough to the object to see if there was discharge. And you know, as Greg said, we turned on the lights and stuff, and he was supposed to have turned off the voltage. I don't think I asked him to. It was supposed to just happen. But the rest of the story is accurate. I felt the corona on my leg, and it was a Miss Wonderbout transformer. I remember the thing, and I just backed up and asked Greg. Greg told me he had nightmares. I did not have any nightmares from that, but I guess he did. The other thing is, Greg could have said, is how I got into this field. I discovered as doing my PhD in physics that I didn't want to be an academic physicist, and there was a job open at this organization, and I knew nothing about high voltage, knew nothing about dielectrics, and I read a book on high voltage engineering the night before the interview, and 35 years later, here I am. But I still have my hair. Okay, so the reason for the change in the title of my talk is that I was only given a few weeks to write the paper, and having written it, I didn't think about giving a talk. I just thought about, I got to get this paper written. And then having written it and thinking about the talk, I realized that paper could not be the basis of a talk. So then I decided to do something quite different, which is basically take one small part of the paper and expand it into the talk. So I'm going to talk mainly about polyethylene. The first half will be about the phenomenological understanding of high-field conduction in polyethylene. And then the second half, my student, Ahmed, I can never get his last name pronounced properly, is in University of Toronto, has been doing a lot of DFT work, computational quantum mechanics, and we think that we're starting to understand and see how conduction works in polyethylene. And so I'll go into that in the second half of the talk. I've got too many slides, so I better move fairly quickly. Then is that polyethylene has a band gap of about 8 eV. And at 300 K, the thermal activation energy, or the thermal energy, of course, is about 0.025 EV. And so if that were the end of the story, we wouldn't be here, because there'd be vanishingly small conductivity, and the dielectric strength would be really high, and we'd be out of business. So fortunately for us, polyethylene has a thermal activation energy in the range of 1 EV, which dominates the dielectric properties. And of course, these non-ideal properties of polyethylene, as other dielectrics, are extrinsic, not intrinsic. They're the result of what shouldn't be there, and the fact that it's amorphous rather than crystalline, and so forth, so on. And that's one of the things that makes it very difficult to study, is you're not studying polyethylene, you're studying the small amounts of things that shouldn't be there. And that's what I'll be talking about when I get into the density functional theory part. So part one then is the phenomenology of conduction in polymeric dielectrics at high field based on polyethylene. And then the second part is what we've been learning very recently using computational quantum mechanics about extrinsic factors which determine the dielectric properties. So why study high field phenomena? Most people in this room probably know that, but I mean, if we know how to design high voltage systems if there's no defects. And so the fundamental question always is, what's the largest tolerable defect? And that involves the high field phenomena that occur around that defect. And if you don't understand that, then you really can't engineer. And determining the worst case tolerable defect experimentally is extremely difficult. It's very nice to have some theoretical backup for that and to be able to at least give good theoretical estimates, because they're probably going to be as good as the experimental estimates. So the phenomenology now, if we apply a very high voltage pulse to a stress enhancement in a dielectric, either the field's going to become extremely high or space charge is going to redistribute to limit the field. In order for the space charge to redistribute to limit the field, the time constant for redistribution of the charge has to be comparable to the time constant of the applied voltage. And from that, we can derive everything that we need to know. So the time constant associated with a frequency omega is basically the inverse of omega. The dielectric time constant, of course, is the dielectric constant divided by the conductivity, which at high fields will be a function of the field. And then for the charge to redistribute, these two time constants have to be roughly equal, which means that if the conductivity at the space charge limited field where a charge can redistribute is equal to epsilon omega. And this plot just shows a typical Laplacian field and the actual Poisson field, including space charge, which will really occur. So typical dielectrics have a space charge limited field in the range of 300 megavolts per meter, and so the field really never gets above that in dielectrics. Now, if we make the simple approximation that the conductivity is an exponential function of the field with E being raised to a power n, then the space charge limited field, the field at which charge can redistribute, is given by this formula here. And the typical value of n is 1/2. And that has a theoretical basis, which I'm not going to get into, but it does. So if we think about field-dependent conductivity, there's two important electric fields that we can identify. One is the field at which the conductivity becomes field-dependent. And that's basically where the energy gained by a carrier between traps is equal to the thermal energy. Because at that point, the field-induced energy is becoming comparable to the thermal energy and therefore having an effect on detrapping. And so we can estimate that field just from the product of the charge times the field times the separation between traps is equal to the thermal energy. The typical separation between traps from the literature for polyethylene is about 2.8 nanometers. And so you estimate about 10 megavolts per meter. And that's about right. The second important field is the space charge limited field, the field at which you get high carrier mobility. And that can be estimated the same way, but now the relevant energy is the trap depth, which is in the range of 0.8 to 1 eV. And in that case, you estimate a space charge limited field of about 300 megavolts per meter, and that's also correct. So at this phenomenological sort of level, we have a fairly consistent picture. Graphically, we can think of this as the product of the dielectric constant times frequency being a constant, and we have the field-dependent conductivity. We have this one threshold here at about 10 megavolts per meter where the energy gain between traps is comparable to KT, and then we have the other point up here where these two lines intersect where you get the space charge limited field. So graphically, it's quite simple. Now, we can get some insight into these phenomena experimentally using the guarded needle technique, which was developed by Zeller and Pfluger at ABB. This is an example of a needle. This has a 5-micron tip radius, about 30 microns of exposed needle, a couple of microns of epoxy, and then there's chromium evaporated on top of the epoxy to form a guard, so that this thing is guarded to within 30 microns of the tip. This gives you a capacitance of a few femtofarads to the high voltage electrode and allows you to measure the image charge on the needle tip, which results from carrier mobility within the dielectric. So if we do an experiment like this, we've got the needle embedded in the dielectric, we've got a high voltage electrode, and we apply a triangular voltage to the high voltage electrode, we see essentially no carrier mobility up to some threshold field, and then we see charge being injected into the dielectric. What we're really seeing is the image charge on the tip caused by charge motion within the dielectric. And those are two distinctly different things. Now, we normally plot this like this, where here's the voltage going up, here we come to the threshold for carrier mobility, we start seeing the image charge on the tip changing, and this is plotted as the square root of the charge. And there's theoretical reasons. You could look up the papers by Zeller for this being fairly linear. What's interesting, though, is that here's the peak voltage, and now the voltage is coming down, and yet the charge is continuing to increase on the needle tip. And this is a very useful phenomenon because it allows us to determine some things that I'll discuss. Basically, what's happening here is that even though the voltage is going down, the field's going down, of course, the carrier mobility is not going instantly to zero. So the charge is continuing to spread away from the tip, even though the field's going down. And this gives us insight into how the carrier mobility or the conductivity changes with field in this very high field region. So we can, for example, do transient nonlinear finite element calculations and compare them with the measurement. So here's the measurement, and here's a calculation for an exponential of ke, ke to the 1/2, ke to the 1/3. And if you look at these, it appears that the 1/2 fits best with the measured data. But it certainly, the n is bigger than, well, n is less than 1 and probably greater than 1/3, somewhere in the range of 1/2. Another interesting aspect of polyethylene is that the space charge limited field is symmetric whether the tip is positive or negative. And it's not at all obvious why that should be the case, but for polyethylene it is the case. These are data, again, measured by ABB for the space charge limited field. And it's a statistical distribution because on a 5-micron scale, polyethylene is not homogeneous. On a 10-micron scale, it tends to be much more homogeneous. But you know, we typically use 5-micron needle tips, and so you see but these two distributions are very similar. So in each case, what we're looking at here is numerous measurements of the space charge limited field with the needle, and each measurement is made at a different point on the polyethylene, on a virgin sample, and it's the first measurement. And so this says that you can inject a space charge density in the range of 4,000 coulombs per cubic meter or withdraw it equally easily. Or to put it another way, you can inject holes or electrons equally easily. So in summary, the high carrier mobility induced space charge limits the field around a stress enhancement. For a 5-micron tip radius, we can get charge densities in the range of 3,500 coulombs per cubic meter. The space charge limited field is around 300 megavolts per meter. And given our understanding of these phenomena and the models that we've developed, we have a reasonable ability to engineer these materials under high field conditions. For example, we can develop a theoretical basis for the worst case tolerable defect in transmission class polyethylene. Now, the experimental data are real, but the question is our interpretation real? We talk about traps, but what generates traps? We talk about a mean distance between traps of 2.8 nanometers. Where does that come from? We talk about an activation energy of 1 eV, but what causes it? And we can inject or positive or negative carriers with equal ease. Why? So P, of course, is a technical material. It's got antioxidants in it. It's got substantial chemical impurities in the range of 0.1%, including things like carbonyl, vinyl, double bonds, and of course it's semicrystalline. So the questions then are, you know, where does the activation energy come from? And that's what I'm going to talk about now. So this work was done by Ahmed at the University of Toronto and my colleague at the University of Connecticut, Rampi Raprasad, who's an expert at density functional theory, was very instrumental in the work as well. So density functional theory is the most common implementation of computational quantum mechanics today. In principle, it's exact, but The actual implementations of it mathematically involve a lot of approximations. It does some things very well. You can predict bond angles, bond lengths, typically within 1%. It does other things less well. For example, the band gap of a dielectric is generally underestimated, but the positions of the impurity states above the valence band and below the conduction band are generally well represented. So there's sort of the overall gap is off by a couple eV or about 20%, but the positions of impurity states are pretty well represented. So the problem then is, as I said earlier, conduction in good dielectrics is extrinsic. It depends on imperfections. So we're going to have to be talking about what these imperfections do. We think normally in terms of a trap-mediated, field-assisted, thermally stimulated conduction, basically Poole-Frankel kind of model. And so the question then, in a conventional sense, is what are the impurity states? Where do they come from? And how do we get carrier mobility? I mean, you can show from fairly fundamental principles that the carrier mobility along a polymer chain has to be many orders of magnitude greater than the carrier mobility between chains. So the real issue is how do you get carriers between chains? So this is just a typical Poole-Frankel model, which is probably familiar to most of you. I won't go into it because I probably don't have time. So this is the orthorhombic unit cell of polyethylene. For the most part, we don't do our work in a crystalline model because things are over-constrained. You know, most of the impurities are going to occur in the amorphous regions, not the crystalline regions, and they cause distortion of the structure in ways that cannot occur in a crystalline region because of the constraints of the lattice. So most of our work is done in a core shell model like this, where you have a core chain. What you're doing now is looking down the chain. So the two carbons, the yellows, are offset, and you're looking down the chain, and then surrounded by a shell of others, and we put our impurity on the core and then calculate the properties. The overall length of the chain is 40 carbons. You need 13 carbons to basically come to infinity. And we want to put something in the middle, so we need at least 13 on each side, so we work with 40. It's a large model. There's over 800 atoms here, and that's, you know, calculations on something like this take anywhere from a few days to a few weeks. But you're doing it on an 8-core workstation that costs $2,000, so you can afford to have a few workstations, and it takes a lot of time to analyze the resulting data. So if you've got 3 workstations, you're probably busy. So this shows a section of a crystalline a crystal model with a carbonyl in it. The red here is the oxygen atom. And you can see there's very little distortion. You really can't see any distortion. Whereas this is the core, the shell core model, and there's the carbonyl, and you can see this shell chain bending around it. You can see distortion of the bonds in the core chain in reaction, so forth, so on. There's a lot more going on there. One of the implications of that is that distortion of the carbon bonds adjacent to the carbonyl generates hopping states very close to the conduction band. So this black line here is the density of states for atoms close to the carbonyl, and the dashed line is the density of states from atoms far away from the carbonyl. And we can see that the distortion of the bonds near the carbonyl, and this is not the oxygen states itself, are generating this hopping state just below the conduction band. You do not see this in a crystalline model because there's not enough, you don't get the distortion. This shows the electron density without an impurity. That's oxygen up there, but it's out of the plane, so we're not seeing its effect. And you can see that basically the dark red here is close to 0, and there's no electron density. So this is basically the square of the electron wave function, giving the probability of electrons in space. Now, one unusual aspect of polyethylene, as far as we know, I mean relative to other polymers, is that the vacuum state is just below the conduction band. The experimental value is 0 plus or minus 0.5 EV. Our calculation is minus 0.36 EV, which is consistent with that. One of the results of that is that in the conduction band, you tend to have states which are in the vacuum between chains and extended along the chain. So basically there's a conduit for electrons to move in the vacuum until they get trapped and between traps. That's not the case for holes. Now, one of the first things we did was to study iodine and polyethylene. The reason for studying iodine is that iodine increases the conductivity of polyethylene by typically something like 4 orders of magnitude, and it reduces the activation energy from somewhere in the range of 1.2 eV down to about 0.8 eV. And these are really big effects. And our feeling was if we can't understand these, we have no hope of understanding what carbonyl does. So we started off on iodine, and here's the iodine I2 in between the chains. This is the core chain, and there's a chain behind it and in front of it and above it and below it. And you can see the I2 here. And what the iodine does is introduce impurity states in the band gap at 0.7 and 0.9 eV. The red here is the density of states caused by the iodine, and the black is the total density of states. So the difference between them basically is being caused by polyethylene. The other thing that it does is it introduces a mixed impurity state at the valence band edge, which is about 50% polyethylene, 50% iodine, and, as I'll show you, delocalized. So you've got you can generate a hole by moving an electron from the valence band up to the impurity state, and then that hole could move either because the impurity state was delocalized, spread between chains, or because the hole created in the valence band is delocalized, and so the hole moves. So either the electron could move in the excited state, or the hole could move in the valence band. In this case, it turns out it's the hole that can move in the valence band. So this is a typical valence band state. I don't know how this shows up there. Oh, shows up better than it does on my screen. Good. So this is well localized. A typical valence band state is quite localized to one atom, in this case the carbon. But this is the mixed impurity state, which is created by the iodine. And you can see this is, again, the probability of the electron in space. And you can see that it's spread over several chains. So basically, you could move an electron up into the hole trap, create a hole, and then you've got a state in the valence band which is delocalized and allows for carrier mobility between chains. Now, this is the iodine state created in the band gap. So this is this state right here, probably the 0.7 EV state. And again, it's well localized. So basically, we've got two things here. One is we've got a mechanism for generating holes and also lowering the activation energy, because these states, the 0.7, 0.9 EV is below where the states are in polyethylene from common chemical impurities. I'll show you later. So we have a mechanism for generating holes, we have a mechanism for lowering the activation energy, and we have a mechanism for carrier mobility of holes. This shows the charge density with the I2 in there, and you can see it spread among numerous chains. Basically, the I2 is highly electronegative. It's sharing electrons with adjacent hydrogens, and this is distorting the electron distribution within the system and spreading it out among chains. Now, people say that the I2 goes in there and it's not bound. It's bound. The binding energy is about 0.3 EV per iodine atom. And it's fairly well bound in there. And this also, the fact that it doesn't come out suggests that it's fairly well bound. Now, looking at basically the states that we're talking about, we've got the valence band maximum. We've got this mixed impurity state, which is extended between carbon chains. We've got the 0.7 EV, which should basically generate the activation energy, and we've got a 0.9 EV state. So these are basically hole traps. We can create holes by moving a carrier from the valence band or the mixed impurity state up into one of these states here. And we've got a mechanism for basically moving charge between chains. On the conduction band side, nothing's going to happen. The iodine introduces a state at about -4 EV. It's a very deep trap. It's not going to have much effect on anything. So all of this is consistent with what's known. Putting iodine in increases hole mobility much more than electron mobility. It lowers the activation energy to the range of 0.8 eV, and it increases the conductivity substantially. So it's a qualitative picture, but it's a relatively consistent picture. So now going to chemical impurities, we can talk about things like carbonyl, vinyl, double bonds, conjugated double bonds, hydroxyl. We've looked at all of these. Those who are experts in polymers will recognize that not all of these are very likely. Some of them were done because as Ahmed did this, he got the feeling that he could predict the impurity states based on the type of bond and the hybridization of the bond. And so he was doing predicting that what was going to happen and then doing the calculations on unlikely impurities just to see if he was right. And he's right. So we think that we're going to be able to publish means for predicting the impurity states which doesn't require doing the calculations. So if we look at the core shell model again, with we can, carbonyl, vinyl, there's a double bond in here, right in here. And we can do the same kinds of calculations, and this is a composite of what these various things do. So if we look at the carbonyl, it creates a hopping state just below the conduction band. It creates a trap state below the conduction band by about 2 eV, which is probably too deep to be very interesting. And then on the above the valence band, it creates a state at about 1 eV. Double bonds create a state in about 1 eV below the conduction band, as do vinyl groups. And this state around 1 eV above the valence band is contributed to by double bonds and also vinyl groups. So we've got states basically 1 eV above the valence band and 1 eV below the conduction band. And we've got some hopping states just below the conduction band. And this shows schematically. So above the valence band, we've got states, the carbonyl, vinyl, and double bond, all very close together between 0.95 and 1.05 eV. And on, okay, so I'm going to talk about this in a little. Now, basically, charge can move between backbones in 2 ways. One is the hole can move in the valence band if there's a valence band state that's extended between chains, or the electron can move in the impurity state if the impurity state's extended between chains. In this case, for example, if we look at the carbonyl group, the hole trap, it's extended between states. We can see that there's, this carbon, there's a probability of the electron. Now, and if we look at the electron density again, we see that carbonyl, because the oxygen is electronegative, it's sharing electrons with these hydrogens and extending the electron density between the chains. Likewise for vinyl. Double bond does not do that. Now, when we go to the electron side, we've got the conduction band minimum, we've got the vacuum level a little bit below it, and then we've got the vinyl and the double bond. Now, here we don't need to have extended states because the vacuum level itself is extended. So basically, charge can jump, hop up into the vacuum level and back down again. Now, where exactly the vacuum level is, our calculation says 0.36. These calculations are not accurate to 0.1 EV. Certainly not to 0.05 EV. So, it could be a little bit higher. It's probably not much lower, but the experimental data, as I said, is 0 plus or minus 0.5. But in any case, again, we have a mechanism for charge basically hopping, and we can identify why the activation energy is in the range of 1 eV. In this case, the conduction band state, again, I showed you this before. There's this state in the vacuum between chains which is extended in space. This shows one slice, this shows another slice, and as you can see, that state extends through the slices. This is the carbonyl state below the conduction band. It's not that interesting because it's 2 eV deep and probably not of much physical significance. This is the vinyl group electron state 1 eV below, and it's fairly well extended as well. So it also provides a mechanism for mobility. So what have we learned? Our calculations are consistent with a vacuum level, that physical disorder caused by impurities generates shallow hopping states around 0.4 eV below the conduction band. Some impurities cause overlap of the electron wave function between adjacent polymer chains. And the data are consistent with the known conduction properties of polyethylene. I think we've identified the states between 0.95 and 1.05 eV, which for above the valence band and below the conduction band, which determine the activation energy. They're relatively symmetric, which may be the reason that the high field properties are symmetrical in polarity. And we've shown consistency with what's known about iodine. So I think we have a fairly self-consistent picture at a qualitative level. So the next step is to go from qualitative to quantitative, which is not going to be easy. It's probably possible for the activation energy because that's more straightforward, but it's going to be much more problematic for conductivity. And of course, electrode effects in some situations are very important. And we've just started working on calculating what happens at the interface between various metals and polyethylene. But it's complicated by the fact that, again, you have to include the impurities. Because, of course, the surface of polyethylene is likely to have a lot more carbonyl than the bulk, and that's where the metal is. So if you don't include the carbonyl in there, you're probably not going to get the right answer. So, questions?
Questions for Steve? Yes, sir. Could you please state your name and identify your organization?
Henrik Herman Gnosis. You've talked about impurities in your model, but you haven't mentioned branching at all. Tertiary carbons, which are going to obviously play a part in this game.
That's true. You could include, okay, so you're thinking of side branches. Yeah, that's going to make life difficult in this model because it would probably be hard to include them in there. The model would become too large. I mean, if you look at historically how this situation has evolved, I would say the last major effort in this area was by Quirk, which was done, I think, as part of the Artemis project in Europe. And if you look at what he did, he was confined to much smaller models. And this was done, I don't know, 5 or 6 years ago. Today, we can do about 1,000. 5 years from now, we can probably do 10,000. So when we get to that point, we can start looking at more realistic models. You're right. We're limited in what we can do.
Nancy, but could you go to use one of the microphones, please? Yes. Because then everyone can hear the question.
That's right.
Hi, Nancy Frost with Krempel. My question relates to materials you're talking about were primarily crystalline in structure.
No, they weren't. I was talking about a core shell model, which is not crystalline.
Okay, so you were handling the interface between an amorphous portion of it and a crystalline
No.
portion of it?
That you're not going to do today.
That's what I was. I'm
Yeah.
like that. Would
No,
be nice
I mean,
to understand.
if you look in the literature, there's a suggestion. I think it was Ieda's work that at that interface there are some special states at around 0.4 eV, and we're not going to model those today.
Okay,
maybe 5 years from now, but not today.
But that's where I could see this is leading to that. I was curious if you thought about
Yeah,
it.
yeah, no. I mean, again, we started off trying to model sort of truly amorphous polyethylene, and we very quickly came to the realization we weren't going to do that. First of all, the molecular dynamic of creating such a model just became prohibitive, and so forth. So the core shell model is a reasonable representation. It's maybe a little bit under-constrained relative to the crystal, but if you do both the crystal and the core shell, and if you're getting a good correlation, then you have a solid feel that what you're seeing is real. I mean, one of the things I didn't emphasize is that in doing this kind of work, You don't just plop it in there and get an answer. You do things very systematically. You start off reproducing the bond angles and the bond lengths from the literature. And you go step by step by step, very carefully building up the model, making sure everything's consistent with everything that's known at every stage. And it's very time consuming, and you have to do this very rigorously. Within these programs, there's many, many variables that you can vary in how you do it. You're basically expanding orbitals and basis sets, and you can use different basis sets. You can use different extension, numbers of within the expansion, so forth, so on. It's
great work. I really appreciate it.
Well, no, I mean, hey, give the student credit, okay? It took him a year and a half before he stopped making mistakes in how he did things. Now he never makes mistakes in how he does things. It's only a question of what we're trying to do and what we're trying to learn.
Thank you very much.
Okay, Rainer Patsch, University of Siegen. Congratulations to this excellent work. 30 years ago now, I got my PhD on conductivity in polyethylene. At this time, I made a computer model to simulate it, and I took only electrons and tried to get to simulate the results I got. Measurements up to 200, 300 keV per millimeter. I agree with your results. A few keV per millimeter, it's ohmic, and then it changes. And space charges start at around 25. And the interesting point, when I tried to simulate to model my experimental results, also anomalous discharge currents and so on, you know this, I think, I came up with deep traps in the region of 1.2, 1.3 electron volts, and with a hopping in shallow traps around 0.25 electron volts. I didn't know what it was. Well, I made some assumptions with self-polarization and so on, which changed the Poole-Frankel effect. But basically it came up with these two different levels, and now we know what it is. Congratulations.
Hopefully. Thank you. Hopefully.
George from University of Southampton. Steve, in the introduction bit, you mentioned several times about the trap separation distance, which is about 2.9 meter sort of length. And how do you think that will come from this model?
Yeah, I didn't address that. I probably should have. It's very simple. If you assume that the density of impurities is in the range of 0.1%, that just falls out. That's about the right distance for an impurity level of 0.1%. If you just, if you say 0.1% and and you look at the number of carbons that's going to be and the separation of carbons within the chain, you get about 3 nanometers. So it's consistent with the level of impurities which we think is there, which is there. Well, yeah, and if you look in the literature, there's work by Perlman, for example, where he's measured the conductivity of polyethylene as a function of carbonyl concentration, so forth, so on. I mean, the data are there. Okay, wait.
Wei Jingying from GE Research. Yeah, first of all, this excellent work, I think, help us to understand from the deep fundamental thing. But from the practical view, we talk about cross-linking polyethylene. So we have a lot of peroxides for cross-linking, and I have some radical groups. So I'm just wondering, how that will affect your modeling results, because when you calculate those vinyl group or carbonyl group is attaching to the backbone. In reality, a lot of impurities, just additives, it's not connect to the backbone.
Yeah, I mean, obviously there's a lot of something like ergonox 1010 in there as an antioxidant, as well as the cross-linking. Yeah, there's a lot of things there. We could, an ergonox molecule is a big molecule. Simulating that alone is a pain in the neck. So putting that into something like this, we're probably not going to do. Some of the smaller molecules you might be able to put in there and look at the effect, as you did with iodine. I mean, if it fits in a reasonable way, you could do that. But again, this has taken the student, he's near the end of his PhD, maybe a half a year away. So this is 3.5 years worth of work. Starting with a student who was an electrical engineer and basically knew nothing about this. But yeah, so the next student, or maybe me. I've debated about becoming a student in this area.
I think, first of all, yes, very interesting presentation, of course.
Introduce yourself, Giancarlo.
Giancarlo Montanari, University of Bologna. Okay, I repeat, very interesting presentation. But a question coming out from this discussion. If you change impurity level, density, for example, going from PE to XLPE, or even having PE with some more impurities than, different technologies, is cleaner, more clean, less clean, and so on. The levels that you showed before about the level above which we have a dependence of activation energy on electrical field and the top level above which we have high conductivity, will they change significantly, do you think? Because I would like to understand how we can engineer these materials from taking care of what you said.
I mean, obviously what we were looking at is one impurity at a time, which is, now we have looked at multiple impurities. And as long as they're more than a couple of carbons away from each other, they don't interact. So, you'd have to get the density pretty high before the probability of having two impurities close enough to interact becomes significant. So at that level, thinking about individual impurities is reasonable. How you take these data and put them into a quantitative model of conduction, of course, is the big question. And that we have not yet approached. This is where we are. Some of these results are only a week or two old. And, where you go from here is the big question. I'm not sure I answered your question, but...
Okay, any other brief questions? Okay, well, I think on behalf of all of us here, we want to thank you for your lecture, Steve, and congratulations again.
Thank you.